Okay, welcome back. This is 3.7, graphing linear inequalities of two variables. All right, so first thing that we want to talk about in this section is an ordered pair some x and y is a solution to an inequality of two variables hopefully those variables are x and y, otherwise your x and y are not x, y, or whatever the variables are. But it's a solution to this if when x and y, those values are replaced in, you get a true statement. When substituted in. Okay. So let's see that in action. If I have an inequality involving x and y, we want to see if a particular point is a solution. Is the point 1, 4 a solution to the inequality? Let's say 3x minus 2y is greater than or equal to 10. So I just plug in. X is 1, so this is 3 times 1. Minus 2 times y is 4, so 4. Is it greater than or equal to 10? And on the left, I'm just going to get some number greater than or equal to 10. It's either true or it's false, right? So this is 3 minus 8. It's greater than or equal to 10, but 3 minus 8 is negative 5. And negative 5 is not greater than 10, so this is not a solution. No. Not a solution. Okay. What about the point, let's use the same inequality and check 7, 2, right? I'm going to erase the work that I did here. Yoink, gone, gone, gone. We're checking 7, 2 now, so 7 gets replaced in for x, so that's 3 times 7. Minus 2 times y, which is 2 now. It's greater than or equal to 10. Once again, it either is or it is not. This is 21 minus 4. It's greater than or equal to 10. 21 minus 4. 17 is greater than or equal to 10. That's true. So the point 7, 2, yes, it is a solution, right? Now, there are many solutions, right? I found one solution, but when we're talking about this, there's typically humongous swaths of solutions on the two-dimensional plane. So we typically will represent the solutions as graphs, right? When we talked about one-dimensional or inequalities of one variable, we talked about intervals, because it was very easy to describe, oh, from here to here or here to here. Right? When we have two dimensions, it's not as easy to describe anymore, so we draw it, right? And describe it pictorially, right? So let's draw one, and let's take a look at, say, let's go 2x minus 3y is greater than or equal to, let's go 6, something easy to start. Now, in order to graph this, the very first thing I want to do is graph the boundary. And in order to do that, I want to replace the inequality. In this case, it's a greater than or equal to, I want to replace that simply with just an equal to figure out where that line is. There's going to be a line. I need to figure out where that line is because that's the very outer edge of my solution space. So let me graph over here. Okay. Scooch this over just a bit. Okay. So I want to graph, in this case, I want to graph 2x minus 3y equals 6, right? That's my boundary. But if I use the intercept method, right, what happens when x is 0? I just divide by negative 3 to get y is negative 2. If I let y equal 0, I just divide each side by 2 to get x equals 3. Okay. And I'm going to plot those 2 points. But not the line yet, right? Because the line can either be a dotted line or a solid line. And so I'm going to put this as a solid line if my original inequality is inclusive, which is if it's a greater than or equal to or less than or equal to, and it's going to be a dotted line, dotted or dashed, whichever, if it's a strictly greater than or a strictly less than. So in this case I have greater than or equal to, that means it's going to be a solid line, so I'm going to make this a solid line. Right? And then I have solutions that are either in all of this area up here or all of this area down here. It's one or the other, so I just have to check. Right? So to check a point, and my favorite point to check is 0, 0. If it's not on the line. Not on the line or on the boundary. Right? If 0, 0 is a solution, that's above this line, that means everything up here above the line is also a solution. If it's not a solution, that means everything up here is not a solution and everything down here is. So that's why I'm going to check this. I'm going to erase this now. If you need this, pause it, because here it goes. So I'm going to check 0, 0. Plugging in 0 for 2 times 0 minus 3 times 0 is greater than or equal to 6. But that's all just 0 is greater than or equal to 6, which is false. And since it's false, this is not a solution up here, and therefore everything down here is. This is going to look terrible because I'm graphing with expo marker here, but all of the region down here, that's my solution space up to and including this line. Pick any point down here, throw it in, it's going to be a solution, right? So that's my solution area, all of that down there, right? Okay. Let's look at a couple of these. Let's do another one. Let's graph, let's say 3x plus 5y is strictly less than 15. Okay. So I'm going to go through these steps. I'm not going to write them down. I will talk them through. I'm going to start with my boundary. The boundary is imagining that this is an equal sign. And then I'm going to do it by the intercept method. If x is 0, I just divide by 5 and get y is equal to 3. 1, 2, 3. If y is 0, that's gone. Divide each side by 3 and I get x is 5. When I go to throw my line down, I know it's going to be dotted because it's a strict less than. And so I have a dotted line that goes like this, right? And I'm going to check that 0, 0 because 0, 0 is not on my line. So if I check 0, 0, I get 3 times 0 plus 5 times 0 is less than 15. The reason I like 0, 0, because this whole side is just 0. Right? It's quick, it's easy, gets rid of a bunch of stuff. 0 is less than 15 is true. That means this is a solution, which means everything down in this region is also a solution. And so that is my solution area, and that's my graph. Right? Good. Let's look at another. Let's say I have y is greater than 2x. Now again, I'm looking at the boundary here, right? The boundary is at y equals 2x. And if you remember slope-intercept form, this is like y equals 2x plus 0. So I can graph that using the slope-intercept. I have an intercept of 0 and a slope of 2, meaning I go up 2 every time I go over 1. Up 2, over 1 more, right? So I have this line. It's a dotted line because it's a strict inequality. And so I look like this. Now when I come to check my point, I can't use 0, 0 anymore because 0, 0 is on this line. I can't use that, right? So I have to check something else, and it doesn't really matter where. I just have to step away from that line, and I'm going to step over here to the point 1, 0. And I'll test 1, 0. Y is 0, so that gives me 0 is greater than 2 times 1, but that 0 is greater than 2, and that is false. Remember, if it's false, that means this is not a solution. Nope. But everything over here is on the opposite side, and therefore my solutions are all of that area up to the left. Right? And that's my solution there. Okay. All right, let's see here. We can, of course, see a couple of, there's always those weird ones that we've seen, the horizontal and vertical lines. If I want to shade in still a two-dimensional system, but I have, say, y is greater than 2, right? I mean, really, this is a one-dimensional system because there's no x here, but if we're still talking about 2 dimensions, then we can still graph this. Y is greater than 2, I'm going to pretend that it's y is equal to 2, find 2, and I know that it's a dotted line because it's a strict inequality, right? Pick a point. Hey, look at that, 0, 0 is not on this line, I can still go through this process. Plug in 0, 0, there is no x, so there's no 0 going in for x, but there is a 0 for y. 0 is greater than 2 is false. If it's false, I shade the other part, and that makes sense. Y is greater than 2 is all of those numbers up where y is more than 2, right? And that's my graph. We can likewise see something happen with x. Let's say x is less than 3. Here's 3. I know that that's a dotted line here. Plug in 0, 0. 0 is less than 3 is true, so I'm going to end up shading to the left. Right? So even though we have one-dimensional systems, we can still graph them in 2 dimensions. It's really, if you imagine collapsing that y dimension down, it's an interval up to 3. We've just then whoosh, gone the other way and expanded this into the second dimension, right, if you will. All right, so those are those 2 lines. And I think that's it for this one. So thank you, and that's it for chapter 3 as well. I'll see you again for chapter 4.